Green.
All right, welcome everyone. So for today's Cut seminar, we're very happy to have Cheng Chin joining us from across the street. Cheng is leading an experimental group at U Chicago working on cold atoms, and they've done some really amazing works over the past years on basically kind of engineering experiments and engineering Hamiltonians that they can study in their cold atom systems. One of their specialty is to shake the atoms with an optical lattice and to increase the interactions in these systems. And they've been able to see a lot of cool many-body physics by doing this, like long-range order and quantum phase transitions. And they've also been working a lot on imaging techniques to actually see what the system looks like. And I think this is what Cheng will speak about today. So take it away, Cheng.
All right, thank you very much. So let me share my screen. All right, so I need this, not the first slide, but let me go back to my first slide. All right, right here. I realize this is a group with theory experimentalists, and but as experimentalists, I'm always happy to show you the result from physics as well as some technique I'm developing. So before this talk, I talked to a couple of students of mine, and the younger students seem to be very interested in this. What are the new capability we have in our lab that different from the conventional kind of approach to quantum gas. So I decided to focus on this topic, which is more the technique we develop. And for theories, okay, I prepare some question for you. Okay, you can this toward the end. Okay, think about how we can possibly kind of beat the uncertainty principle to reach the resolution much higher than the wavelengths of the light. All right, so this is my title: how to get a super resolution imaging microscopy of these atoms in optical lattice. All right, I think this is the pointer. Yes. All right. Okay. Right, so just introduced by the host. Okay, we've been working on this quantum simulation based on core atom systems, and trying to address some of the interesting issues that is difficult to address, difficult to resolve, or difficult to simulate, okay, to understand in other fields. And then also sometimes we have some fun trying to develop new type of this, identify new type of quantum dynamics. So in the past couple of years, I've been looking into field body bound states, okay, related to thermophysics and nuclear physics. And some of this dynamics in people's study in cosmological models, circular oscillation, Kipple mechanism, low radiation, and so on. More recently, the fireworks just mentioned earlier, look into the emission of jets, there's a stimulative process on the quantum gas that can be connected to the jet substructure people study in particle physics, and also simulation of this lattice gauge field based on Fourier engineering. And also related to condensed matter, we study critical behavior of the quantum gas near the phase transition, magnetism, magnetic domains, or mediate interactions, how in that condensed matter or high energy physics, how particles can talk at a distance, say you power potential, Cooper pairing, and so on. With some undergraduate experiment looking into levitation of kind of generic particles. All right, but today I will be more talking about this about imaging, and I'm going to start the story with this photo. This is taken 10 years ago. Okay. All right, and the guy, the old guy in the middle, okay, is George Smith. He graduated from University of Chicago in the 50s. And when he got the Nobel Prize, I think 2009 or 2010, okay, we didn't even know that he graduated from here. Everybody who knew him probably already not here anymore. All right. So, but we're surprised to hear that he graduated from here. So we invited him come come back to give a talk and to show, and also invite him to visit a couple labs. And I was one of the faculty member who did kind of this asking to come to my lab and see what's going on. And he was very happy that we are using CCD in the lab. And I was kind of astonished by that comment. Okay. So, and this is a business card he passed to me. You don't even see doctor. You don't see anything in his title. Okay. He's actually captain. So what happened is after he graduated from here, he joined this I think that was the a national lab, okay, developing this semiconductor devices, okay, and Bell Lab, I believe, okay, and work on this CCD for a couple of years, and then eventually, I think he mentioned develop 4x4, 16 pixels, and said, I'm bored. There's no point to go on, okay. So pretty much he retired soon after that. And since then, he has been kind of switching his interest to selling. So he started a second career, and he decided he want to have his own boat, want to sail around the globe at least once, okay, with his wife and so on. So by the time this the Nobel Prize was announced, okay, he already retired a second time. He even finished his second goal of life. And then we just one day, he told me that he went to the bar he used to meet his crew and the watermen and so on. All right, and pointed in the TV. Hey, you see? Do you see that? Yeah, that's me. And nobody had an idea how he could possibly. Nobody even knew that he was a doctor. Okay, how he could got the Nobel Prize. So he was very happy to see that we actually use this CCD in the lab. I say, well, come on, if just tell me any lab that has no CCD. Okay. But he's very happy we can really see atoms with a CCD that he invented. Right. So this is the experiment I show him. We guide the atoms, okay, through this long thin skinny tube, and then with a CCD on top of the system to look at the distribution of the atoms. And this, actually, I had to say at this point, this is pretty much the foundation of our research for the past 10, 15 years. We were able to push the resolution of to look at these atoms down to the length scale that's small compared to correlation length of the quantum gas. So while you're looking at this roughly about 20, maybe 200, about 200,000 cgm atoms cool down to the ground state, okay, in the circular box, okay, the circular box. And then we had the resolution down to about 1 micron, and the correlation is something that we can really see just from the fluctuation, from the inhomogeneity or density distribution. Okay, and maybe you dream in, okay, you can start to see, well, okay, there's the fluctuation, the noise is just the density subtracted by the mean. You show a lot of structure as a function of what? As a function of interaction between the atoms. If you prepare the atom with higher density or with a stronger kind of scattering length, then system can transition from a weak coupling regime to the strong coupling regime. And we can see directly from the CCD, from the images, the correlations are changing. Okay, yeah, because we're the resolution better than correlation length. So this lay down the kind of this foundation for a lot of experiment. We can really probe into such a short length scale to look at how quantum gas behave and the transition dynamics and so on. So obviously also this need to have got a lot of help from this lot of students working on different part of this high resolution imaging. And a lot of young students, when they first come to our lab, they also kind of this thing about imaging. There's a new capability, high resolution you can reach, and so on. This is another example, okay, that how we can this group from Marcus Greiner and Harvard, the 1 year after that, they will also demonstrated that they can reach down to single particle, single site, single lattice. It's now called quantum gas microscope. So you look at a many body system, say in this case, maybe also thousands of atoms and so on. And then you can go down to every single particle and see how they are distributed, how they are correlated, and what kind of pattern they form in the lattice. Okay. So when I work with many students, one of the things that's a common misconception is that if you want to get a high resolution, all right, you just need to get a better camera to have more pixels. We got this probably from the improvement of digital camera and or the resolution of the camera in the cell phone. You think, okay, higher resolution means that you just need to get more pixels to get higher resolution. Okay. So whenever I say, well, let's try to, if you get higher resolution, then the younger student, they will come back to me and say, well, then how about us get a better camera? But that is not really the case. Fundamentally, the resolution of imaging is not given by the pixel size. You can always go down to smaller pixel size. They maybe one day go to nanometer pixel size. That doesn't mean we can see things down to nanometer. Because the more fundamental limit on this, how well you can resolve and say any object. So that's assume we have 2-point masses, 2-point sources. Okay. All right, if you use the optical beam to optics to try to resolve them, you can use a microscope. Okay, and then you are going to see that no matter how, however good the CCD you have, okay, you are not going to see a point source. There's always a finite resolution, and that finite resolution, is given by the so-called, this depend on the definition given by the wavelengths and also your experimental kind of setup also. So this resolution formula depends on how you want to define it. So one of the common limit is called Abel limit. Okay, that is, if you have 2-point source, then one is red, one is blue. Okay, and then the point source will appear to have a finite width. So you can see the arbitrary kind of definition what you mean by resolution. In this case, Abel limit is when the 2 peaks are added together and you can barely resolve. You can barely see there's a gap between them. There's also Rayleigh criterion. Also, there's a spiral limit. That's when the kind of minimum completely disappear. Okay, so these are all technical. Okay, you can see just the coefficient is different, but what's important is the scaling. It depends on the wavelengths. The shorter the wavelength you have, then the higher resolution you get. And also depends on this numerical aperture. Okay, that's a dense in-depth refraction, more by the angle, half the angle that you have the viewing angle. Okay, so this is this optics. Okay, this is object. Okay, the 2 theta. Okay, defines theta here. Angle defines theta here. Okay, and you can imagine when the theta, say, how large can theta be? The angle can reach 180 degrees. That is a theoretical limit if you only look at the system from one side. So sine 90 degrees will be 1. And assuming in-depth refraction is 1, then you can see the limitation is the lambda over 2. Okay, so if you look at the system with wavelengths of 1 micron, then the resolution will be limited to half a micron. You can also see this as a result uncertain principle. Okay, given by the uncertainty of the momentum, the light coming from different angles, then there's an uncertainty of the momentum in the x direction. So therefore, that leads to uncertainty in the as a Fourier transform. Then you are given this uncertainty in the real space. Okay, right, and I think you understand the uncertain principle. In this case, is a result of Fourier transform. All right, so that seems to be the limit. If you want to, you try to use a wave to look at the particle. All right, but however, people are not satisfied with this. If you try to look at things that are smaller, and have been over 10 years, people have developed kind of this super resolution microscopy, okay, to look at, say, bio or chemical biomolecular system. So on the left-hand side, this is one demonstration from the so-called STORM, stochastic optical reconstruction microscopy. On the left-hand side is what you see from the basic, the standard microscope. The resolution is a wavelength divided by 2. So in this case, about 250 nanometer. All right, so you can see something, but but what they can do is that with the same photons, okay, they were able to now reach down to 20, 30 nanometer, almost is essentially a factor 10 or better than the optical resolution. Okay. All right, and one trick, okay, this type of super resolution microscopy is based on the idea is that let's try to excite some of the molecule. We know molecule are very small, okay, and then we cannot see the size of the molecule because we are limited by optical resolution. Okay, but once you have good enough signal, you can try to determine the central mass of this block. Okay, all right. Just say I have this economic pointer, I can determine the central mass once I have even though the size is finite, the size is 250 nanometer, the spread is 250 nanometer, but I can determine the center to much better than that. Okay, so by a factor 10. So what they can do, every time they just excite a small subset of the particle in the image, determine the central mass, and do it again with a different subset of the particles or molecules in this case, and determine the central mass. And repeat this process many, many times. Eventually, they accumulate this all the light sources, okay, that are these molecules, and every time you can determine the position to, say, 20 nanometer. So this after kind of compiling many, many images, okay, of the image on the left side and try to determine the position of molecules. Under the assumption that each molecule behaves like a point source. Okay, so all you want to determine is a central mass of the point source. Okay, so this certainly allows you to resolve some smaller feature. However, this assuming there's a normal structure, okay, and the nanometer scale, every molecule is a point source. But if you wish go down to the wavelength or to go down to the wave function, say a quantum system, then you will not be satisfied with the with that assumption. You want to see whether there is any structure, okay, from any light emitter, whether the light emitter is a real point source or it has certain distribution. Then we need to go to the second type of super resolution imaging. Here is also this is called stochastic. What I've just mentioned is called stochastic super resolution imaging. If you implement something like this on the atoms, so for example, this is a demonstration, okay, based on ion. There are only 2 ions in the system, and you can see the optical resolution will give the kind of uncertainty also about, say, a few hundred nanometer. However, with a good enough signal, they can determine central mass to 1.7 nanometer. Okay, that they know the location to better than much better than the wavelength. The wavelength is about half a micron. Okay, and I also know this technique won the Nobel Prize in chemistry, okay, by these 3 physicists a couple years ago. Right now, the second type is deterministic. Deterministic microscopy is saying that I'm not going to assume my light sources are all mathematical points. I really want to see whether there's a distribution. For example, there's a wave function. Even the fundamental particle, the wave function might not be fully symmetric, might not be a Gaussian. Why, if you really want to see the structure, okay, of the light source that is at much well below this wavelength. So the second idea, instead of trying to look at trying to kind of illuminate this particle with a regular photon that excite the atom, and then you see the emission of the light. Okay, here they try to go to multi-photon process. So basic idea is that this time you can try to excite these green molecules, okay, using red photons. So 2 red photons will make up for the difference between the ground and excited state. And then you can get the green photon out of it. Or you can try to extend this to multi-photon process. Okay. So fundamentally, this what this means, you think about the interaction between photons and atoms, because now you require multiple photons. So you can imagine in the kind of interaction Hamiltonian, what you have multiple operators in order to excite the atom, okay, or excite the molecules. So each photon, for example, look at this, the 3 red photons on the right-hand side. Each photon can be focused to, say, a Gaussian distribution like this. But now you have 3 photons, you have 3 of them. So you have 3 operators. So their wave function, is the product of 3 Gaussians. So you can see the coefficient as a 3 in front. So effectively the resolution reduced by square root of n, square root of 3 in this case. How do you want to go to? All right, very good. Okay, so you can see if a multi-photon process, you can improve by square root of n. So I mean, all right, if I want to improve the resolution by factor 10, all I need to find a 100 photon process. Will that be possible? Theoretically possible. You can always you all go to it's a nonlinear dependent. You go to very high intensity or kind of spatial atom molecules that can be possible. However, okay, this is not quite likely for kind of a typical material. So let me mention what's a way to get nonlinear process. Nonlinear process, similar theories here, is similar to you have a kind of high order kind of interaction process. If you think about in the field theory, in the field theory language. All right. So how do you kind of illuminate this? How do you convert, say, the 2 photon process? So here's one example. We send a blue photon to the material and get 2 red photons out of it. So eliminate 1 blue photon, create 2 kind of red photon. This is a nonlinear process. Okay, and this will not happen in regular material, right? Certainly, it wouldn't happen in vacuum unless your photon is strong enough, okay, to kind of lead to some kind of QED effect. Okay, but for the regular photon, the optical photon, there's no way you can see such kind of nonlinearity. All right, so even in the material, we need to find various, and typically the efficiency is not very high. So you need to have a lot of intent. You need to go to very high intensity, okay, to get this to enhance this nonlinear processes. For coatoms, we are in the other limit. Coatom, you know, is a gas, and we're talking about the density that is many order of magnitude lower than the density in any material, any solid state material. We have much lower density. At the same time, the typical kind of light intensity we illuminate on the atoms is also order of magnitude weaker. So everything goes the wrong direction. A much lower density of atoms and much lower light intensity. So it looks like it's impossible, okay, to see nonlinearity. Just like in the air, if you want to illuminate the air with some light, it's possible you can see a nonlinear dependence, okay, with a kind of weak light. You'll see this is impossible. All right. So we like to be able to go to high resolution. We like to do deterministic super resolution microscopy, but our target is extremely dilute. Okay. And typical intensity is also much weaker. How is this possible for us? So this posed as a question to our community, and we found a solution about 2 years ago. So can pause here for a minute. I think we'll understand how atom interact with light. How is it possible we can go to high, develop some very strong nonlinearity with low intensity and a single atoms. All right, so I'm going to introduce us one idea that we come up with. So I'm showing this process. I think it's called optical pumping. I think got the Nobel Prize also in the 60s. Okay. All right. So I'm showing this. First, let's consider 2-level system. In our case, we're talking about CDM atom, the ground state, Okay, there's a f equal to 3, just some kind of quantum number. And then we turn on the light. Okay, you go to excited state. Okay, and excited state with a different quantum number 4. Okay, so and this is a simply twofold. This simply kind of a transition between two levels. There's a non-linearity. Okay, and the ground state label is 6s. Excited state 6p. Yeah, if you're not in atomic physics, you don't need to worry about these jargons. In the beginning, let's assume with all the particles in the lowest state, so 100% f equal to 3. Okay, and then after we do the excitation, we turn on the light. Okay, atom can be excited to f equal to 4. Okay, and then when atom excited to f equal to 4, then it can decay to f equal to 4. This is the other ground state. And then we can perform imaging, and then we perform imaging to see what's the population we have in the f equal to 4 excited state. Okay, this other state. That's all you need to know. Actually, you don't even need to worry about this imaging process. I'm going to hide them. Just remember we can measure the population. Okay, in f equal to 4. So if you turn on the light, atom being excited, there is a fraction of the particle that can decay to the state we want. Let's call that fraction beta. And then, for simplicity, that assume all the other atoms will decay to the initial state. Let's assume this is a 3-level system. Okay. And the process can be classical. Let's consider classical process for simplicity here. Okay. All right. And then after the decay, some fraction go into f equal to 4, some go to f equal to 3. Beta 1 minus beta, so the sum is still 1. All right, you can do this again. And the second time, you excite this particle to f equal to 3, from f equal to 3 to f equal to 4 again. Okay, this time you kind of transfer for those particles that go back to 3, you can try to push them to excited state again. The second time, okay, then you are going to get then you get a bit more into f equal to 4. Okay. But again, it's also possible even the second excitation particle can decay back to f equal to 3. And that probability is now 1 minus beta squared. So if you don't really need to follow this algebra, I'm just showing one example. Let's assume for the first photon, yes, 60%, 40% going to the target state and going back to initial state. Okay, and now the second photon is essentially 40% square, so you only left with 16% in f equal to 3. The third photon that will be 40% to the third power. So you can see, just take a few photons, you are essentially push all the population from the initial state to the final state. And this is optical pumping. So you require few photons and few photons enough to polarize the population to the final state, to your target state. And this is important to put it on the side. That remember, this is a highly efficient process. You require more than one, but typically few photons. In our case, it's roughly about 3 photons, and that's enough to polarize the most of the atoms to the target state. And that is the target state we can measure. So how this has anything to do with imaging? Okay, this is all about internal degrees of freedom, and how this has anything to do with nonlinearity. Okay. All right. So if I can just write down I can do the math analytically, you can show that the population in the final state will follow this exponential dependence. All right. You can see that this is exponential process. Essentially, that if you go to a slot machine, every time you the 10% you will lose your money. You can play enough time. Eventually, you're definitely going to lose everything. Okay, so your property result goes down exponentially. All right, so you can work out the math and put in all the parameters from the property of the atoms, okay, and so on. Okay, but the important thing to see that now you do have an expression that is no longer linear in intensity. Intensity right here, but it's inside exponential function. Okay. So well, this is not so there is a nonlinearity here, even though the behavior is rather trivial. You eventually saturate to 1. It's not the kind of nonlinearity you have in mind. For I squared, I cube, and eventually will kind of diverge. But nonetheless, all we need is a nonlinearity. So now this issue is that this with a function like this, whether there's how can we take advantage of nonlinearity here, and how can we use that to get a much higher resolution, get this deterministic super resolution image. All right, so this process is simple that almost everybody at least in the working on this atom in the life probably know this in the kind of in the first class. Okay. All right, and then we figure out a way how to use this to kind of get the super resolution image. So here's a simplified experimental setup. Okay, to give you an idea how we do this imaging in 1D. Okay, so that dimension in x direction is x. Okay. For simplicity, let's consider one atom localized somewhere. Okay, and we are using the trapping beam to localize, but for now, forget about that beam. Just assume we know there's one atom is a localized, and then this is a wave function of the atom. Okay. Now, optical pumping, that is this red beam. Okay, for those who are not experimentalists, okay, just imagine there's a beam coming through the atoms, and then there's a cube. Okay, that's the wouldn't bother you. But there's a mirror. Okay, you know the mirror will do just reflect the beam. Okay. All right, so I made a cartoon right here. The mirror provides a boundary condition, so you're going to get a standing wave. So this pink line is the intensity pattern, okay, of this along the x direction. So once you turn on the beam, we get a standing wave. Obviously, the atom will be quickly excited, right? Because there's some intensity on the atoms. And we just mentioned only few photons will be enough to push the atom to F equal to 4. Okay, and that's why we can measure it. So you will take a very, very short time, typically less than microsecond, atoms are polarized will be pumped. Okay, so now this the mirror, there's something called piezo. Piezo, just think about this, something we can control the position of the mirror, okay, with high resolution. So you push the mirror by, say, a fraction of a micron. So you push the mirror, that change the boundary condition, the standing will move with it. Now you push the atom to the side. However, atom will still quickly go to F equal to 4, okay, because there's not enough photons. Okay, 3 photons is a very few number. I think all of you know this is easy to get a lot of photons. Okay, photons are not that expensive. However, if we can go all the way, if we can really tune the nodes of the standing wave right on top of the atoms, now the situation is different because there's no light. When there's no light, atoms are not excited. Okay, so as long as atoms within this very narrow window where atoms see less than 3 photons, atom will have a higher probability to stay in F equal to 3. If we can align the atoms or align the node exactly with the atoms, in principle, atom will stay. Then you will see no excitation. Okay. All right. So to conclude, atoms are safe within this narrow window. I use this green band. This green band is the spatial region where the atom do not even see 3 photons. Okay. And now what can I do? I can try to increase the intensity, or I can try to make the exposure time longer. Then the band, the narrow band, the atom do not see 3 photons cannot be arbitrarily narrow. Okay, as long as atom move away from it, say even move by a few nanometers, okay, then with sufficient exposure, the atom will see 3 photons, they'll be excited. Unless atoms are exactly at the node. Okay, unless atoms are exactly at the node, there's no photon, there's no nothing. Okay, atom will not be excited. So essentially, you can imagine this window is behave like a probe into the position of the atoms. Okay, and then that probe has an arbitrary narrow window, no longer limited by the wavelengths. Then we can start to ask the question whether we can make this window so small, such as small compared to the atomic wave function. Our atomic wave function might be nanometer in size, but how about that make the window as small as 1 nanometer? Okay, then what will happen? Wouldn't that just equivalent that we are really probing this atomic wave function, with a nanometer resolution. All right, so that's the idea. Okay, and at the end of the talk, we'll try to pose a question: how do we break the uncertainty principle? Okay, so if you don't care about experiment detail, you can think about what is the fundamental limit, how can we possibly kind of get well below wavelengths. All right, but for the people who are interested in the experiment, this is a more kind of this is a complete diagram of the experimental setup, where the light that we use to trap and also use to pump the atoms. Okay, and then where piezo to control the two beams, the red beam will go through, and the piezo will control the position of the red beam, the boundary condition of red beam, and blue beam will be used to localize the atoms. We also another piezo to control the position of the blue beam. Okay, so we can control the position of the atoms. We can also control the optical pumping, and then we can this is a complete setup. Okay, I'm not explaining this the other detail, the wave plate and so on. If you're interested, I'll be happy to answer your question, or you can also find that in our paper. All right, so quickly go through the experiment. Do we really see such kind of nonlinearity? So this is the experiment. So what do we see? In our experiment, we try to measure the optical pumping efficiency by evaluating, by looking at how many atoms are excited. So what you see in this image, all atoms are excited, unless we really overlap the node with the atoms. Now we see a large number of atoms not excited. Okay, so this is the upper row of this image is what we see from the experiment, and the lower image we try to quantify the behavior of the system and looking at the response for low intensity, high intensity, very high intensity, higher and higher, but all these are very low. Okay, one saturation intensity is I think is even weaker than the sunlight. Okay, so now for very, very low intensity, remember when this intensity, when I is very low, you can always do expansion. Let me show the theory curve. Okay, you are given something like this. Okay, you say we want to see nonlinearity, but intensity is really vanishing is small. Errors will be linear, right? So you can see that for very, very low intensity, we see a linear dependence, and this more or less reflects the sinusoidal behavior of the standing wave. However, when you go to some intensity right here, the proper energy scale to compare is a so-called saturation intensity here. When you go to get closer to the saturation, now we start to see a very narrow peak. Okay, right? And we can analyze this narrow peak. Okay, better. Now you can see that the structure or the width of the peak is now dropping well below the wavelength 800 nanometer. Okay, and this is exactly because when we go to higher intensity, we get a window, the window within which atom can see 3 photons or less, smaller and smaller. And we're opening up a smaller and smaller window to plot the atomic wave function. Okay, so by increasing intensity, we can see kind of our resolution continue improving. Okay, even though the theoretical expectations we should go down, the window should have no fundamental limit. However, we are already seeing a saturation where we were limited by the ground state wave function. Okay, how well we can localize a particle in the lattice. The ground state wave function is, in this case, about 50 micron. So therefore, the size will also be 50 micron. Okay, if you want to show that we have an even higher resolution, we will need to do some math to deconvolute the wave function size and our image resolution to get to, essentially that means that we need to go to smaller feature in order to prove that we have an even higher resolution. All right, but nonetheless, I think right here it shows that we can get down to tens of nanometer. Right, so I'm going to show one kind of this interesting application. Okay, so what can we do? Remember, before this work, people can only see kind of few hundred nanometer. So now we can go down to tens of nanometer. We can start to see the dynamics, okay, of the particle within one lattice site. Okay. So this dynamics at a length scale comparable or small compared to the size of the wave function. Okay. So the one simple way to set out the dynamics is showing on the left hand side in panel A. We essentially will quickly kind of release a particle, okay, on the slope, and then the particle slide down in the classically you can see imagine particle going back and forth, okay, and this typically happen in the kind of tens of microsecond scale, and that is so we can resolve them. You can see the particle we see indeed going back and forth. Okay, we indeed see this the particle are oscillating, okay. And but if you look more carefully, you also see this oscillation, okay, seem to be damping out, also seem to have some other structure. So it turns out even a simple oscillation in the lattice is not so simple, is some complication. So this is a numerical simulation based on single particle in the lattice. Now we're talking about in real space, you can push it and see how it oscillates at a length scale comparable to the wave function, so on. Even from our simulation, it seems to suggest some kind of a weird behavior. In the simulation, there's no dissipation. Okay, we just kind of evolve Schrödinger's equation with one particle. Okay, that's localized to begin with. You see, why do we have such kind of weird behavior? Okay. All right, and you can see there's some kind of the structure kind of resembles what we see from the experiment. So you say, well, this is a single particle physics, not too exciting, but this is already interesting. This the level we see something unexpected. So one thing we can do is that let's try to, for example, let's draw a sine wave. We know semi-classically the particles should oscillate like a sine wave. Okay. Indeed, if you draw a sine wave, you can see more or less kind of go through all the kind of maximum. Okay. But you can also see the intensity not really uniform along the green line. So something else is going on. All right. So what can we do? As an experimentalist, we can try to we can try to trace. You can see there is you see there's something here, there's something here, something here, something here, right? There's some other structure. So let's try to draw a second line that more or less follows all these the faint feature, okay, we see in addition to the green line. So if I draw the second one, okay, it turns out have essentially the same frequency, which is not surprising, but we need to have an offset in phase, almost like a pi phase. You see when the green one goes to the left, the blue one also go to the maximum. Okay, let me go back so you can be more convinced yourself. Okay, this is the blue line, more or less kind of showing this the other structure. This is blue, and this without the blue. Okay. So what's going on? Can put for now I can only provide our this hypothesis. Okay, what's happening here? Why do we have a second oscillation? Okay, so let me know if you agree. So you think well semi-classically we are just pushing the particle away from the ground state, then the particle should be oscillating. Okay, that's a harmonic oscillation. However, when particle going on to here, it's also likely particle internal. So this experiment, I want to have a want to think perhaps it's easier for particle to turn on when particle move all the way to the here is a classical turning point because the barrier is now smaller. It's a shorter path to turn on to the other side. Okay, and that happens in all sides. If this is happening, then you can imagine this. You can imagine this. Then the red particle will oscillate back and forth, and this gold shadow will also oscillate back and forth. Okay, but tunneling probability is not very high. Okay, all right. So and then there will be 180-degree out of phase. Okay, All right, so let me know if you agree with this picture. Okay, so this is one thing that we can see. There's interesting dynamics of particle oscillating in the lattice. Okay. So now let me talk about the second kind of interesting observation from this experiment, which is also nice.
Can I ask a question?
Sure.
So in these plots you showed us of the experimental results, so you're measuring at every time using this technique.
That's right.
Every horizontal line is a measurement, and
yes.
And this doesn't affect somehow the particle, these measurements.
Right. So what we do is that for every single time we perform the measurement, okay, by changing the piezo location. Okay, mm-hmm. And after imaging, then repeat the experiment again.
Mm-hmm. Okay. Right. I see. So every dot is an experiment on this.
That's right. Every small square is one experiment.
Okay.
Every small square, one experiment. Okay. One independent experiment, all based on different atoms. But we also always give them the same initial condition, okay, before we release them.
Okay, thank you.
All right. Okay, the second interesting behavior that we didn't expect. Okay, that's one good thing about this doing experiment. There's always something new to discover. So that is, we are this. Remember, we localize atom in the trap, in the blue lattice, and then we probe the atoms with the optical pumping in the red lattice. But now let's just think about, you have two gratings. All right, grating is something that has a periodic structure. Okay. In one of them, that has a periodicity of 852.37 nanometer. The other one has a periodicity 852.34 nanometer. This turned out to be the wavelength we use to trap and to pump. So what does that mean? That means if you compare the lattice constant, in one case is 0.37, the other 0.34. The lattice constant mismatch by 30 picometer. Can we control that? Yes, we can. Controlling this mismatch by 30 picometer turns out it's pretty easy for us. Okay. So when we go from one side to the next side, these two lattices kind of offset by 30 picometer. So that means if you look at more carefully where they overlap, okay, you can see around here, along this stripe, the two black lines overlap. Okay, so you see a black, white. But some other location, see the white line overlap with a black line. So if you overlap these two gratings, now suddenly you see 100% black, right? Because they are out of phase. And here they are in phase. Okay, you see the stripes. Okay, now you don't see the stripe because they are out of phase again. And then every lattice only offset by 30 picometer. In this case, we need to offset the two grating by as long as 2 centimeters in order to rephase. Okay, in order to rephase. So suddenly we bring we're creating a new length scale that is macroscopic. Okay, and macroscopic, and that's something we can control just by fine tuning the wavelengths of the laser at the 10 picometer scale. All right. So what does that mean? Now here's another cartoon. Now imagine with a localized atom in this in the blue lattice. So atom here, and because this lattice is periodic, so the wave function, okay, is also periodic. So this is a wave function of the blue atom, the wave function like blue, okay, and the red line is the red lattice with a very narrow window, with a super narrow window that we can probe the atomic wave function. So in the beginning, they do not overlap, so we see no signal. Okay, but then because every time there's a mismatch, every time the lattice constant mismatch by 30 picometer, we're getting now you see the red one slightly and very gently and slowly catch up with the atomic wave function, and when they catch up, now we're atom hiding in the window. Now we start to see our signal. Okay, at some point, Okay, when there's a mismatch between the red and the blue, now the signal disappear again. Okay. So it turns out we see this signal, if you only look at the red dots, nothing. Here is a large overlap, see a signal. Here, the no overlap signal drop back to 0. Turns out this shape is reflect the original wave function with a magnification that we control by a factor of 1,000 to a factor of million. We can essentially expand the atomic wave function in the nanometer scale to millimeter scale. Nanometer millimeters is a magnification 1 million. And that's something we can do. Okay, so this another way to think about this, just like if a piece of, I don't know, beef. Okay, but now you make a very, very thin slice and then expand them, so you can start to see the structure in front of eyes. Okay, but it's coming from a very thin, many thin slices. All right. Okay, so this second idea, how does that help? So now we can start to control the mismatch between these two lattices. If you made that stuff on the right hand side, if you made a mismatch large, this 500 gigahertz, that is how we characterize the mismatch in the laser frequencies. Okay, if you're not do some kind of jargon. All right, the gigahertz, 500 gigahertz mismatch. Now we start to see the signal will rephase or come back again. And each one of them essentially reflects the wave function in one lattice site. If you reduce the kind of frequency mismatch, okay, that means it'll take a longer distance to rephase. Now we can amplify this nanometer scale to a much larger, almost millimeter. Okay. Eventually, if we go to very, very small kind of mismatch, we're amplifying nanometer scale. This equivalently 100 nanometer will be here. However, in our image, this is 4 millimeter in size. Okay, so you see the this atomic scale and our scale on the CCD. Now you can see there is a enormous magnification. Okay, so to verify that this moiré microscopy does have the capability to amplify this atomic wave function by factor 1,000 to million. Okay, we can do such kind of microscopy compared to the piezo kind of scheme I talked about first. We can also use a piezo to do a very fine scan in real space by nanometer. So these two experiments by moiré and also by piezo scan essentially reproduce the same kind of atomic wave function. Okay, and that kind of validate or justify this moiré microscopy indeed is showing the atomic wave function, even though right here wave function kind of simple. This is just a wave function of particle in the lattice. All right. So I'd like to conclude, okay, with our this technique. We're able to show that this full head maximum we can now reach down to 30 nanometer. If you want to compare that to the use this Abbe limit, I think it's more like kind of 16 nanometer. It depends on how we define what resolution is. And if you want to use a stochastic super resolution imaging, only want to determine the standard mass, okay, then we're only limited by a simple noise. In that case, we can pin down the position of the atom to better than 1 nanometer. Okay, and all these are realized based on atomic wave function localized in the ground state of this lattice. That is a typical wave function of few 10 to 100 nanometer in size. The second advantage of this imaging is that it only takes a microsecond to perform the imaging because it only requires 3 photons. Only 3 photons are needed. And for atom to interact with 3 photons, that is it takes a microsecond or less. And then this is a bonus, this kind of this moiré magnification that we realize can help us to magnify nanometer structure to millimeter from a single image. All right, but this is based on the assumption that the wave function periodic. Okay, so that's why we need the lattice. All right, so we've shown you some dynamics, and also I'd like to pose the questions whether this technique can be useful to see some kind of many-body wave function. Now you can go to a nanometer or tens of nanometer. For core atom, that's quite enough to see, for example, pairing or some correlation or orbital in the lattice side. So that may be a very, can be a powerful tool to probe some kind of a non-trivial kind of structure, okay, or the wave function within one side. All right, so let me see how much time do I have. Okay, so essentially that one last slide, I think 2 minutes. Okay, how do we beat the uncertainty principle? Okay, so let me remind you how uncertainty principle. Okay, so but before I go there, I'd like to thank my group members. Okay, the experiment done by a former postdoc, Mickey McDonald. Okay, graduate student Jonathan Tristandi and this Kevin Yao, Kai Shuang Yao. Okay, and also other students are working on the other quantum simulation project. I'll be very happy to talk to you about those as well. All right, so let me go to the last slide. How do we beat uncertainty principle? First, that's to understand the Abel limit can be easily derived based on uncertainty principle. The uncertainty we can determine the position is linked to the uncertainty of the momentum in that direction. Okay, and then this is just I rewrite the Heisenberg uncertainty principle that by just delta x delta p, you divide h bar from both sides, then you just see this 1/2 on the right hand side. And but this is not is pretty straightforward. Okay, uncertainty in the x direction is given by the size of the lens. Okay, that tells you the photon can come from different directions, and you can from there you can determine this is you can determine the Abel limit. All right, if that is the case, how is it possible we can improve this resolution down to tens of nanometers, which is more than a factor of 20 or 30 below the wavelength? Okay, so you might remember this is the formula we've been using. We talk about nonlinearity and so on. You can also say that's just a smoke. Okay, so all nonlinearity make it look fancy, but you can see what exactly is the resolution we get. Okay, based on this, you can derive the resolution looks like this. There's some constant that's kind of we can throw the constant that doesn't matter. Okay, there's also the wavelength. Okay, 2 pi, that's a constant, that's throw that away. And then there's a 1/square root of intensity multiplied by time. If you increase the intensity by a factor of 4, or increase the time by a factor of 4, then the photon number will increase by a factor of 4. Okay, this well that makes sense. Okay, then just say if you perform the experiment, kind of repeat the experiment many times. Okay, and then this the photon number, okay, what goes in will help you to reduce the statistical uncertainty. However, my question to you is that, but in our case, we know that atom only scatter no more than 3 photons, then the process will stop. Okay, if you really think about this kind of scaling, turns out you can derive this n is 180 in order to reduce the resolution by that much, going down to the tenth of nanometer. But fundamentally, our atoms scatter no more than 3 photons. They'll go to the other state. The whole process stops. Okay. All right. So you say, how is this? Where is this scaling coming from? And what's n here? Okay. It turns out we only need 3 photons. Does that also necessarily mean that in reality you only need 3 photons? You can actually go down to arbitrary resolution. That can really break this uncertainty principle because we only need 3 photons. Okay, all the other photons just go through without interacting with the atom. Second question: if you really know this, the true fundamental limit for kind of many body system is that this it should be improved by the total particle number. If you really think the photon number plays a role, okay, instead of 180, why don't we have lambda over n instead of lambda over square root of n? Or fundamentally, how do we get improved by another square root of n to reach down the true quantum limit? Certainly, this process I'm talking about, optical pumping, doesn't sound like a quantum process. Okay, would there be a true quantum process that can really take the full advantage of the photon number, okay, to reduce the resolution by 1/n? All right, I'll leave this to you so you can think about what's going on here. So with this, I'll thank you for your attention.
All right, let's thank Cheng for the very nice talk. And we have some time for questions.
It's okay.
Looks like everyone is shy.
I have got my hand up.
Oh, sorry. Yes, I had noticed. Yeah, go ahead.
I wonder if you could say something about the Efimov effect.
Sure. Okay. All right. Let me go back to my slide. Am I showing? Okay, I'm not showing. Okay, I guess I'm not showing here. So let me see. Okay, so ephemeral effect is the one that will look into this how atom can cluster into three-body bound states. Okay, and I guess I need to go very far back. Okay, so we are doing this experiment with a quantum mixture with boson and fermion. There's a prediction how this kind of mixture can be used to see the three-body bound states. All right. So what we have been able to show is that we can identify kind of several ephemeral bound states, and trying to check that whether there is a predicted geometric scaling. Geometric scaling means if you find one bound state has a size of lambda, okay, the lambda is not wavelength, just some kind of some number. Say the one bound state has a size of A, then the next lambda, the next quantum state will size of lambda A. Yet there'll be the next one, the lambda square A. Okay. So they will follow geometric scaling. In our case, that scaling factor is 5. So that's the latest experiment on that one. We demonstrate that we can indeed see 3 bound states and look at the length scale, and indeed they follow this roughly follow this scaling. One 4.9 and the third one close to 24 or something like that. It's rather close to the prediction. Okay. All right. And the second thing we did following that is trying to show that whether this behavior is universal. There's been a lot of argument in nuclear physics as well in co-atom physics trying to show that this whether there's a universal scaling for this kind of 3 or 4 body bound few body bound states. Okay. And when this based on our work, we look at different type of molecules, okay, in the lithium CGN system, we were able to show that there are kind of the system not quite universal. There's some kind of non-universal contribution. Okay, if you compare different set of ephemeral states. Okay. I'll be happy to tell you more about this whole series of kind of study on this that I'm not talking about today. I'll be happy to, if you email me, I can tell you more about what we have been doing.
Okay, thank you.
Okay.